I'm really excited to be here, and thank you everyone for taking the time to attend this session. I'm gonna try my best to use these 90 minutes to give you a solid introduction to structural equation modeling and try to really draw on connections that SEM or structural equation modeling has for improving or helping you in your research of human system interactions. And so to motivate this talk, I actually, wanted to learn more about human system interaction research, and I came across a publication from the National Research Council, and this was specifically about human system integration in the system development process. And I thought this part of this quote was really interesting. It says that system designers, like people in general, can be subject to an
You're muted, Laura, for some reason.
Oh, was I muted from the beginning or just now?
You could start over on the quote.
Okay. I don't know what happened. All right. So yes, this quote was really interesting when I came across it from the National Research Council. And it says that system designers, like people in general, can be subject to an overconfidence bias, focusing on the potential benefits of new technology while failing to anticipate the complex interactions and new problems that may emerge. And then the authors go on to say that there is an urgent need for improved human system integration methods and tools that will enable system designers to anticipate and head off potential problems earlier in the design process. And so I think that, when these folks are talking about the importance of improved methods and tools for HSI research, my hope is that SEM is going to become an additional tool for all of you to use in your work precisely to improve upon your research in this area. And so the structure for this tutorial is, I'm going to start with an introduction. I will assume that you don't have previous experience with SEM, so we'll talk about what it is, and I'm going to draw specifically on the connections it has with factor analysis and regression analysis. And we're going to talk about path diagrams because they are a fundamental tool that are part of SEM that make it very easy to interpret and specify structural equation models. And since this is 90 minutes and we're in a virtual environment, I thought that it would be very boring to just speak for 90 minutes in sort of a lecture style. So what I'm going to do is we're going to work through some applied hands-on examples. And I chose a data set that I think everybody can relate to. The data are about perceptions of COVID-19 threats. And so I'm going to introduce the data after the introduction, and we're going to learn with those data how we go about specifying and interpreting structural equation models. And because I want to take a very applied approach, I'm going to list a few specific questions that we're going to tackle with these data, and we're going to just work through them. And that's going to lead us to talk about two very important techniques of SEM. One is confirmatory factor analysis, and the other one is called path analysis. And to wrap it up, I'm going to show you some examples on that I did a literature review where I was looking at how SEM has been used already in this field. And so we'll look at some examples in case you need some inspiration. All right. So structural equation modeling is a framework where both factor analysis and regression analysis come together. And from the factor analysis side, what we gain is the ability to measure the unobservable. All right. Oftentimes we call these latent variables. And from the regression analysis side, we gain the ability to examine relations across variables, whether they're observed or not observed directly. And so when you bring both of these things together, you have a very flexible framework, which is SEM. And so what I think is really important to understand is that SEM is not just one statistical technique. It's in fact a framework where all sorts of statistical techniques can be specified. They can be fit. Things like multiple regression, path analysis, even your good old ANOVAs, t-tests, it's a framework where all of these types of models can be estimated. And there's more that, this is not an exhaustive list. But the ones that we're going to touch on today are multiple regression path analysis and CFA, or confirmatory factor analysis. Now, I thought it was interesting, for all of you in this presentation, I would invite you right now to just type in the chat real quickly, what are some unobservable variables that you wish you could measure or that you're interested in measuring in human system interactions research? I'm just going to pause for a second to give you a chance to type it all in. I know there's about 50-something participants in the audience. So can you think of variables that we don't observe directly? There you go. We have attitude towards vaccine. Absolutely. It's very difficult to tap onto an attitude, right? Because we can't observe it directly. That's a great example. Human trust, 100%. Yes, trust is difficult to measure. Yep. And there's a couple of folks who thought of that same idea, right? User trust of a system. Workload. Yes, I came across that as well when I was doing my literature review, trying to learn more about human system interactions research. These are all great examples. And so, in fact, when I was trying to learn more about this field, I came across, and I just put a list here of a handful of variables that are not observed directly that seem to be very helpful to be able to measure in this line of work. Things like perceived performance, satisfaction, quality, trust, and mental workload. And someone else talks about connectivity. Absolutely, that is also another unobservable variable. And so in the context of SEM, we call these latent variables. And again, in this presentation, I hope that we're going to, I'm going to show you how to go about measuring these things effectively and also how to model them. So the first thing that we're going to learn about are path diagrams. This is really going to be the tool of choice for us, because if you are looking through textbooks or journal articles, I would say 90% of those articles or books that use SEM are going to show you a path diagram. And so we need to understand how to interpret them and how to use them. So SEM, as the name implies, structural equations models, consist of systems of linear equations. And so we have the option of expressing our model through systems of equations, or alternatively, we can use a path diagram to represent the exact same equations, right? And here I have a silly example where, I'm talking about predicting candy taste. And I use this example because I really think that a path diagram is so intuitive that even a child can understand it. In fact, I put this diagram to the test with my 10-year-old. I said, hey, look at this. What do you think this is? And immediately she was like, oh, those are the things that make candy taste good, And so it just goes to show that it is easier to convey our models and our results if we rely on path diagrams instead of the equations. Obviously, there's nothing wrong with the equations, but it's just a nice tool to have. And so what we're going to do is learn about what exactly all the elements of these diagrams represent so that we know how to interpret them. And so the elements of a path diagram are in this figure. The first thing you can see here, there's a rectangle for an observed variable. So those are the things that we actually do have variables in our data sets for, right? If we can observe them, we have a measure for them, and those are going to be represented with squares or rectangles. Circles or ovals are used exclusively for those unobservable variables called latent variables in this framework. And double-headed arrows are used to represent the variance or a covariance of a variable. So the way we know which is it is because if the double-headed arrow starts in one variable and ends on that same variable, then it would be a variance. But if it starts in one variable and ends in a different variable, then we know that's a covariance. Then we have regressions or loadings. And those are represented with a one-headed arrow, all right? So that pretty much sums it up. There is one other shape that you might come across in diagrams, and that is a triangle. Unfortunately, we're not going to be able to talk about the triangle in this presentation. The triangle represents a constant, and it's used to model means and intercepts. There's a really great models for that rely on the means, but again, we're not going to discuss that in the tutorial today. But I just wanted you to know, if you do come across a triangle, that is something that is possible to see in SEM. All right, I also have here to the right some building blocks for how we're going to specify structural equation models through path diagrams. And so the most example, I think, building block is that of a simple linear regression. And what we see in this diagram is that X and Y are enclosed in a square. And so that means that they're observed variables. And notice that X has a one-headed arrow pointing to Y, and that simply means that Y is being regressed on X. It also means that X is predicting Y, right? And notice the double-headed arrows in each of the variables. So the double-headed arrow for X is simply a variance, right? It starts and it ends on the same node, so it's the variance of X. On the other hand, the variance for Y is a residual variance. And we know that because there's a, because Y is an outcome, there is a variable that's predicting it. And so this double-headed arrow represents a residual variance. Now, the nice thing about SEM is that it really is such a flexible framework. So there's nothing stopping us from building upon this model by, for example, adding a third variable. We can call it Z. And in this case, Y could be a predictor of Z, right? And that's a very interesting thing about SEM, is that Y has two roles, is both an outcome and it's also a predictor. And so those types of sequential relations can be specified and investigated in this SEM framework. The other building block is that of a latent variable. In fact, this diagram right here is basically a very, very simple one-factor confirmatory factor analysis, all right? And so the thing to point out here is that we have the latent variable is represented with a circle. It has a double-headed arrow because it has a variance. And notice that the latent variable has one-headed arrows pointed to W, X, and Y, which are observed variables. And the reason for that is because in SEM and in the traditional factor analytic perspective of latent variables, these latent variables are underlying causal variables. They're hypothesized to cause the common variability we observe on the measured variables. And that's a really important definition. So I want to make sure that that's clear, right? That there is a causal assumption that the variability that's in common across W, X, and Y, that those variables co-vary with each other due to an underlying unobserved latent variable, all right? And that's why the arrows point from the latent variable to the W, X, and the Y, to the observed variables. We also have these double-headed arrows for each of the observed variables, and that's because we know that each of them has a residual variance, right? It's an amount of, some proportion of variance that is not explained by the latent variable. One thing I want to point out is that people who have a experience with principal components analysis oftentimes use the term latent variable to refer to components from PCA. And when you come from a psychometric background, that's something that we really want to distinguish. We wouldn't want to use the term latent variable interchangeably for a component. We actually like to keep those terms as very distinct. And so what I want to do is take a little detour, just a one slide detour, to explain the difference between a latent variable from a psychometric factor analytic perspective and from PCA, from a component from a principal components analysis. And so in this image, what I have on the right-hand side is a latent variable from a factor analysis perspective. And notice I'm using this same sort of the squares to denote observed variables, but I shaded them with different amounts of blue, okay, inside the. And so the blue area represents the variance that is due to what we intended to measure. So that's the signal, what we really wanted to capture when we measured whatever it is we were trying to measure, all right? And in turn, we have then another proportion of area in these squares that is gray, and that's basically all the other sources of variance. And that's going to include measurement error and other systematic sources of variance that are simply not what we intended to measure. So notice here in the latent variable, it's all a solid blue. And so that is meant to convey the fact that the latent variable on this right-hand side is capturing all of the common variance across the observed variables, all right? And that is in contrast to the components from PCA. So notice on this left-hand side, the component is a mix of the gray and the blue. And the reason is because the goal of principal components analysis is very different. The goal is dimension reduction, right? It's a great tool for dimension reduction, but the goal then is to extract the maximal amount of variance from the dimensions of our data. And because PCA is going to try to explain as much variance as possible, it's going to have a combination of that variance that is due to what we wanted to measure and also what we didn't really intend to measure, okay? So what that means is if your goal is to measure unobserved variables that are hypothesized to be the underlying cause of what the variation that you do observe, then you really want to make sure that you're specifying latent variables, and that from factor analysis, right? And when we talk about latent variables in this tutorial with respect to SEM, we're talking about a factor analytic perspective. And so I find that is important to make this distinction. And so hopefully for those who are familiar with PCA, this makes sense. All right, so that's the end of that detour. So why would we use SEM? And I have here a path diagram. It already has all of the numbers along the arrows because it's already been estimated, right? This was based on data. And so I find that this diagram has a number of features that facilitate explaining why we might use SEM. And so I have the reasons right below. So on the first bullet point here is the fact that we can measure unobserved variables and we can model them directly in an SEM. Right in the middle here, we have a latent variable that we're calling conflict. And so we're able to estimate and model that variable. And by definition, the latent variables are going to account for measurement error, right? Because remember that the latent variable is only capturing the common variability across the variables it points to. And so it accounts for measurement error, which is a great thing. And also notice in this path diagram, we have a number of relations, right? So there's on the far left, we have this support variable, which is predicting both work and interact. And then both of those in turn lead to conflict. And then conflict has all these other outcomes as well. So there's all these sequential associations that we can investigate. And we can actually answer questions like, what is the total effect that support has on, say, growth, right? So we can look at that whole sequential association and ask, what is the total effect that that variable has? This is something that is very useful to understand the mechanisms by which something happens. Another reason is simply missing data, right? Most real data have some missingness in them, and SEM, I think all software has an estimator that allows us to use the most cutting edge techniques for handling missing data. In other words, even if you have a simple linear regression, if you have one missing value on one variable, the whole row is going to be dropped out of the analysis, right? It's not going to be taken into consideration. But if you were to estimate that simple linear regression in SEM, you're actually able to use all of the data that are available. So no full rows are going to be dropped out. And that in and of itself is a big advantage. And the last and maybe most important thing is to say that SEM allows us to test theories about how variables relate to each other, right? So it's an important point because we have to have a theory coming in. So SEM really is a confirmatory framework. Notice in this path diagram, to specify this model, we had to have some previous expectations, some previous knowledge that to know that support had to be the predictor of work and interact, right? And that these were the predictors of conflict and so on. So we do have to come in knowing something about what we are studying. And so in SEM, we can fit a model that maps onto our theories and then figure out whether the model fits well or not, right? Is there support for our theory? This same diagram is very useful for introducing a lot of jargon that you will come across in SEM. And so I see there's a question in the chat. Let's go ahead and answer that question since it's not a difficult one. It says, what are the assumptions of SEM? For example, must data be normal and must variable relations be linear? So yes, we do assume multivariate normality in the most common case, but there are a number of different estimators that can be used. Depending on the software you're using, you're going to have access to different algorithms. And so there are ways to have nonlinear relations. By all means, you can have nonlinear relations. And you can also invoke certain estimators that allow you to not have the assumption of normality. But the common case is that, yes, there is a multivariate normal assumption. All right, good question. Okay, so back to the terminology. I really hope that, if this technique is going to be helpful for you guys, you definitely are going to have to seek out more resources to continue to learn, right? Because 90 minutes is definitely not going to be enough. And so you're going to come across a lot of jargon, and I want to make sure that we go over that so that you know what all of the articles or textbooks are referring to. So the first is, we talked about observed variables. And in fact, a very common term in SEM is to call those manifest variables. We already talked about latent variables, but another term is that of exogenous variables. And those are the variables that don't have anything predicting them, right? Notice these two here have a covariance, but they don't have a unidirectional arrow pointing at them. So they're not outcomes. And therefore, these are the two exogenous variables in this model. And that's in contrast to all the others, okay? Because all the other variables here are endogenous variables. And that's simply because they are outcomes in one place or another, right? They have unidirectional arrows pointing at them, so they're endogenous variables. The variables that define the latent variables are called indicators. And so these are the variables that are caused by those unobserved causal variables. And notice that they're, those residual variances that we talked about from the indicators, those are oftentimes called uniquenesses. They're also called unique factor variances. And that's because they contain a combination of variance that is systematic, right, that is unique to that variable, in addition to measurement error. Okay, so that I think can get us through the majority of the jargon in SEM, the most common one. So how do we go about learning SEM? I think as I have, it's not the first time that I try to teach some of these concepts to folks that don't have any background in this analysis. And I find that a useful thing to do is to kind of shift our focus in realizing what we're really analyzing, okay? And the thing about SEM is that it really is a multivariate analysis of covariance structures. And it's also of means, but I put that in parentheses because we don't get a chance to talk about means today. But it is a multivariate analysis of covariance structures. And once we think of that, we realize that it has implications for what is really the data that we're analyzing. Okay, we're analyzing variances and covariances. And so to give you an example, here I have a data table, and this is usually how we have our data, right? We have columns to represent variables, and each row here represents an observation. And that's great. This screenshot happens to be of JMP, and I could use that, that data table to launch and run an SEM analysis. It's not a problem. And you can use those types of data, in any SEM software to do analysis. However, under the hood, what you're really going to be analyzing are the variances and covariances of those data. Okay, so I have 7 variables shown here, and they would actually be their variance covariance matrix that are actually going to be modeled under the hood. And so that's really important to realize that that's the data that we're really analyzing. And that also has implications for thinking about the residuals of our models, because those residuals are going to be with respect to that covariance matrix. And I'm going to show you an example of that in a little while. This also has implications for what we think about degrees of freedom. So the degrees of freedom are with respect to that variance covariance matrix. And so usually in SEM, we say that the degrees of freedom are the difference between the knowns and the unknowns. That's the classic way in which people talk about degrees of freedom. And what that really means, if we look at the example that we have here with 7 variables, we have 7 variances and 21 unique covariances that we have from our sample data. And that's what we're basically going to give the program to run an SEM. Okay, so the known pieces of information is what we have is 28, right? Is the sum of those variances and covariances. And then to get the degrees of freedom, we would have 28 pieces of known information minus the number of estimates that we have in our model. And that's what the unknowns represent. All right. So once we shift our focus, then I think it's going to start to make more sense, what SEM is really doing. And this slide is basically my best attempt at explaining the inner workings of this technique. And so what I have at the very top in this first panel is one very simple path diagram. And so the thing about path diagrams, remember that they map directly onto a system of equations. And so I happen here to label the double-headed arrows, which we know are variances. I label them with sigma square, so W, X, and Y. Again, just to denote that these are actually parameter estimates in our model. And so this diagram is actually depicting and implying a structure in the data. It represents our beliefs, our theory about these data. Okay, so the second panel shows exactly what that model implied covariance matrix would be. Notice that the diagonal shows the variances of each of the variables, but the off diagonals are exactly 0. And that's because there's nothing connecting the W to the X or the Y, right? There's no one-headed arrows or two-headed arrows. There's no connection. So basically, this specific diagram is saying that we believe these variables are perfectly uncorrelated. And so that means that our model implied covariance matrix is going to look like what's shown in the second panel. But of course, we have sample data, right? The idea is that we're going to come in and give our sample covariance matrix, right, is going to be what we're giving into our program. And so the values in that sample covariance matrix might or might not be 0 in the off diagonals. In this example, they're not. But what's going to happen is that during model estimation, what SEM is doing is trying its best to match the data from our sample covariance matrix to match our estimates as closely as possible within the constraints that the model implies. All right. So in this particular case, we are going to be able to capture the variances of each of the variables exactly as they are here in the sample covariance matrix. And so those are going to become the estimates of our model. And then those values can be plugged in into the model implied covariance matrix. And we can then look at the difference between model implied covariance and the sample covariance. And it's that difference that tells us how good or bad we did in fitting our model, right? That difference becomes the residuals. So remember in the previous slide, when I said that the residuals are with respect to the covariance matrix, this is exactly what I was referring to, is we assess the fit of the model by looking at those residuals, which is simply the difference between what the model implies and what our sample covariance matrix has. Here, however, you see that the numbers 0.6, 0.53, I mean, we don't know what the scale of the data are, so we don't know how to interpret those, right? Is that too large of a residual? Is it too small? And the bottom line is that there is a way to normalize those residuals. And so you're always going to be able to look at normalized residuals so that you can interpret them and get a good sense as to whether you have too large of a residual or too small. Another thing is that there's a lot of work over the years that has been focused on coming up with indices of model fit that basically summarize in one statistic what's all in that residual matrix. All right, so we do have those model fit indices that allow us to also figure out whether our models fit well or not. Okay, so let's see if you've been paying attention. How many degrees of freedom do we have in this model, right? This it's a very simple path diagram, but remember that degrees of freedom in SEM are the difference between the knowns and the unknowns. So just go ahead and type it into the chat if you feel like it. I'm going to give you guys a second to think about it. It's a good guess. So somebody's guessing that there's 0 degrees of freedom. It's a good guess. It's not right, but good for you for putting yourself out there and giving us an answer. All right, there's another person who's saying 7. You guys are close. You guys are very close. It's not quite. So 3, yes, 3 is the right answer. And let me explain why. So remember, this is, thank you everybody who's making themselves vulnerable for giving an answer. I really appreciate you participating. So the pieces of information that we are giving that we're giving the SEM program are the number of elements in the sample covariance matrix. And in this particular example, because we only have 3 variables, the pieces of information right here, right, I'm going to put it, is our 6. If we count each of the values in this off diagonal, we have 6 values that we're giving in. Those are the known values. They come from our sample data. And then this particular model, notice that there are only 3 estimates that we're trying to obtain. We're only trying to estimate 3 variances. And so the knowns are 6. We subtract the number of estimates from the model, which are 3. And so the number of degrees of freedom in this model are in fact 3. All right. Yes, so hopefully that clarifies degrees of freedom in SEM, which is definitely different from what we're used to, right? Because we're used to thinking about the raw data and the number of observations, the total number of observations in a row. But again, behind the curtains in SEM, we're really working with the variance covariance matrix. Excellent. All right, so this is just another slide that is trying to clarify the process, right? We have a path diagram, it depicts a model, it implies a very specific structure of the covariance matrix. Through estimation, we try to match as close as possible the sample covariance given the constraints from the implied matrix, implied covariance structure. And then we compare those two to get residuals that allow us to assess the fit of the model. So a very important aspect of this process is the fact that we really need to know what is the expected covariance structure given the model that we have, right? So we can draw a path diagram and we can get really creative putting arrows and all this good stuff, but we also need to know what that drawing implies about the covariance structure of our data, right? And so that's what we're going to see next. And I find this following part just really fascinating. All right. The way, or one of the ways, we can always work through the linear algebra, but I really, I'm going to show you what I believe is the most intuitive way to understand the expectations, the implied covariance structure of the data. And we can do it through what are called path tracing rules. All right. So if we have a path diagram that is drawn correctly, we can always trace the paths in order to understand the implications of that diagram for the data. So I'm very proud of this little animation. Let me just play it for you. The rules state that we can go back, we can turn around, and we can go forward. All right, it's really simple. And that's what's really beautiful about this. It's a very simple idea. We always go back, we turn around, and we go forward. And this is something that Sewell Wright in the 1920s, he's the one that found that we could obtain the expected moments of the variables by tracing a path diagram, okay? And I know that this whole go back, turn around, go forward can be pretty abstract. So let me just example. Here's a very, that simple linear regression diagram. And again, I have labeled all of the edges with some Greek letters just to show that those are estimates in our model. And what we're talking about is, for example, if I'm right here at Y, I can go back through this beta path, okay, through this one-headed arrow, I can go back. I can turn around through double-headed arrows, only through double-headed arrows can I turn around. And I can go forward back to Y through that one-headed arrow, okay? So that's what we mean when we're talking about going back, turning around, and going forward, is tracing that path diagram. I'm going to play it again just so you guys memorize it. You go back, you turn around, and you go forward. And that's what we're going to use in order to understand what are the expected variances and covariances in our models. So for variances, the rules say that we have to leave and come back to the same variable. All right, so we have to find all of the possible ways to leave and come back to the same variable, and that will give us the expected variance of that particular variable. For covariances, we have to leave, we have to find all the possible ways in which we are going to leave and arrive at another variable. And I have a note here that we're not talking about means, but there's also rules as to how we get the expected means. Just not enough time today. So we're going to multiply all the paths along the way as we're tracing, and we're going to sum all of the possible ways that we find, okay? So we're going to do this. This is going to work for both variances and covariances. In a second, we're going to work through an example, so just bear with me. Here's the rules, a few more rules. They're very simple. So the first is we can only leave through a double-headed arrow or by going back on an arrow, okay? You can only turn once. There is no limit on how many times you go back or how many times you go forward, but you can only turn once. And then you can only turn around through double-headed arrows. And finally, you can only arrive at a variable through an arrowhead. So let's look at an example. In this slide, I already have the model implied variance covariance matrix for this very simple linear regression. And what we're going to do is first start with X. All right, so if we want to know what is the model implied variance of X, we said that we have to find all the possible ways to leave and come back to X. So we have to start at X and figure out how do we leave and come back to it in every possible way. With X is very simple, right? Because there's only one way to do it. And the only way is through the double-headed arrow. We basically leave the node and come right back to it through that double-headed arrow. And so the expected variance of X is simply sigma squared x, and that's what we have here in the matrix. I cannot leave going through this arrow over here because that would mean that I'm starting by going forward, and you cannot start by going forward, right? Remember the little animation. You have to go back, then you turn around, then you go forward. So I could not go in this direction. But again, I can actually leave by going back through a double-headed arrow and coming right back to the same node. Now, the expected variance of y is a little trickier. The expected variance of y, let's see, we can leave through this one-headed arrow, through beta. Then we cannot go back any further, right? So now we know that we can turn around. So we're going to turn around through the double-headed arrow in x, and then we can go back forward, back to y, right? So we want to start at y and come back to y. And the way we do that is back through beta, turn around through sigma squared of x, and ride back toward y through beta. And that, remember, we multiply the paths along the way. That's what we have right here. The first element of this expected variance is beta times sigma squared x times beta. Of course, I can simplify this just by putting beta squared, but I want it to be very detailed as to what those steps were. And there's one more way in which we can leave and come back, which is through this double-headed arrow, just like we did with x, right? And so that's an alternative way to leave and come back. Therefore, we're going to sum, right? We're going to sum that first way in which we did it, and then we're going to sum that with omega squared y, which is the residual variance of y. Whew, I know this is a lot, but isn't that really interesting that you can really get just through a diagram and through tracing it, you can actually understand the model implied covariance structure. I think that's just really cool that something so simple actually works. So the covariance is the last thing we're going to look at. And remember from the previous slide, we said we leave and we arrive at another variable, and we have to find all the possible ways to do that. This diagram is very simple. There's only one way, right? If we start in y, we can only leave by going backwards. So we go back this way, and then we have to arrive at x. We have not quite arrived though, because there's no arrowhead right at this intersection. So we actually have to go back, turn around, and now we've arrived at x because there's an arrowhead right here. Okay, that's part of the rules. We have to go back, and in order to arrive at x truly, we have to turn around and go forward here. So the covariance is simply beta times sigma squared of x. All right, so we figured it all out. All right, we have the full model implied variance covariance matrix for the simple model. And of course, if we had more time, we would work through a little more complex models. But I just wanted you to have a taste of path tracing rules. I know I've talked for a long time so far, so I want to make sure I give people a chance to ask questions. Are there any questions so far? I'm pretty comfortable with silence, so I'm good at giving long pauses. Make sure, there we go, there's one question. Let's see, can you comment on the difference between SEM and linear regression in the previous example? Absolutely, and that's a very good question, right? So linear regression and SEM, we can use SEM to estimate regression, but they're not the exact same models, right? They're not identical, and that's an important thing to clarify. So in this particular example, notice that X has a double-headed arrow, right? So it has a variance. And just because we have to have that, I mean, in SEM, that's part of the model. And that in and of itself is telling us that we have an assumption on X. We're assuming that X follows a normal distribution. And that's not true of linear regression. We don't have to make that assumption of our predictors, of the distribution of the predictors. And so that's one difference. However, the coefficient from the regression is going to be identical. Okay, so I guess from a practical perspective, there are differences, right? The difference is that we're making more assumptions in SEM, but it is those assumptions, by the way, that allow us to account for missing data in the most elegant ways, right? If we assume normality of X, then we're able to use all of the data that are available. Even if we just have data on Y, we're still able to use that row of data because we're making that assumption. It allows us to not have to throw out that case. And so, yeah, that's a good question. And I'm going to work through an example that actually compares linear regression to linear regression in SEM. And so we can drill a little bit more into that when we do that. So I'm going to say, am I going to talk, I'm going to address model diagnostics. Yes, I will definitely talk more. I think once we get into the examples, I'm going to start pointing much more to all of the diagnostics and model fit and all of that. We assume errors in X and errors in Y are independent. Okay, so this particular, yes, the short answer is yes, but let's see, there are ways in which we can incorporate certain specifications of models where we don't have to make that assumption. In this model, we have to assume that they're independent because we wouldn't be able to estimate the model otherwise. In more complex models, you can actually explicitly model the error of a variable, and you can covary that with something else. All right, and so this is often done like folks who are familiar with instrumental variables and instrumental variable estimation or two-stage least squares. Those types of models can be fit in SEM. So we don't always have to make assumptions of independent errors, although in this particular example we do. All right, great questions. I'm so glad you guys are all participating and engaged. I want to go on by asking you yet again to participate. This time is going to be on a little poll. I set up a poll online. Unfortunately, I think only 25 people are able to respond to my question. That's what I get for using some free service online, but I still think it's going to be fun to do this. So you can, well, let me actually go over to the question. So I hope you can hear. I have a question that I would love for everyone to participate with. So what you have to do to answer the question is you have to send a text message from your phone, text to 22333. And what you have to text is the code for your answer. All right. So the question is, how much of a threat, if any, is the coronavirus outbreak for the rights and freedoms of the US population as a whole? And so look at the different options and the answer that you want to endorse. You go ahead and send a text message to indicate what is your response. Thank you. We already have some answers coming in. Look at that. Isn't this a cool? Yeah, I love to see the live answers. So you'll be able to send your answers, and this continues to update as people continue to answer. Very cool. We'll give it another few seconds for folks to continue to respond. Awesome. Oh, look, we just had another entry right now. All right. And so naturally, as you can imagine, the perceptions of threat of the outbreak are in fact different, right? Because there's going to be a number of factors that are going to influence whether or not we happen to perceive the outbreak as a threat. And so exactly what we're seeing here, there's a lot of variability. And of course, now we have vaccines. And so there might be, a lot of folks who don't feel the threat anymore, but maybe they would have felt it a year ago when there was so much uncertainty. And so thank you, everybody, for participating. Yes, this is really interesting. And I think I have another question here. It is ready for you guys. This one is asking a little bit different. It's still asking about a threat, but in this case is what is the threat for day-to-day, wait, I have to move this, for your day-to-day life in your local community. So how much of a threat, if any, is the outbreak for day-to-day life in your local community? All right, so there's folks who perceive it. Once again, we are finding some variability on those responses. Yeah, and so there's going to be, again, different perceptions on how we respond to this question. We'll let it go live just for a few more seconds. It is interesting, right, that in this particular case, we see a different pattern of responses where so far, at least, everybody's endorsing at least a minor threat. Right? We don't have anyone who's endorsed not a threat, or at least not yet. Not to say that someone wouldn't, but we definitely have a different pattern of responses. Awesome. Well, thank you, everybody, for participating. This is fun little live activity. I love to see those bars moving around as people send in their answers. That's cool. All right, so why did I ask you this? Well, it's a really good way to introduce the data that we're going to use for our examples. And so the data, as I mentioned at the beginning, we all know we're going through some difficult times with the pandemic. And from the very beginning, people were talking about the threat that the virus and the outbreak was for our physical health and, of course, also our mental health. And so in the summer of 2020, so very quickly, this group of researchers, along with many others, of course, out there, have been doing a lot of research about the pandemic. And this particular article was published in the summer. And the authors had what on the surface looks like a very straightforward question, right? They said, how do perceived threats of COVID-19 impact well-being and public health behaviors? And so that seems pretty straightforward. But of course, there's a few problems here. The first one is that this concept of perceptions of threat of COVID-19 is a very abstract concept. We certainly can't measure that directly. Of course, well-being is also an abstract concept, but it's different because we've been measuring well-being. We've been designing surveys for measuring well-being and other types of ways to measure well-being for many years, right? But these folks did not have a survey to capture this new construct. And so what the authors had to do was figure out a way to measure those perceptions of threat, and then they were able to address their original question. What they found is that there's one type of threat, they call them realistic threats because they threaten our physical and our financial safety. And the other type of threat that they discuss is the symbolic threats because these are things that threaten our social cultural identity. And in the article, they actually came up with this survey that they call it the Integrated COVID-19 Threat Scale. And they have 10 items, it's 10 questions, and the first 5 here are to measure realistic threat, and the other 5 is for symbolic threat. And notice that the questions that you participated on are, in fact, one of the items are for the realistic threats, and the other one was for symbolic threats. So I wanted you guys to get a little taste of what it is to answer these types of questions. But that's part of what they did in their study. And so I got the data from the authors, and that's what we're going to be working on to demonstrate some SEM examples today. So we're going to ask or answer very specific questions. The first is, how do we measure perceptions of COVID-19 threats? And we're going to look at those 2 specific types of threats. This is going to lead us to talk about confirmatory factor analysis and how we assess a measurement model. Notice that to really do a good job in designing a new survey, we have to start with exploratory factor analysis, and that is not part of SEM. So I'm not going to talk about it today, but know that that would be a preliminary step where we sort of get a subset of items that we then come to SEM with to confirm or to test whether we can actually use those as a good, survey instruments. The second question is going to be about whether or not the perceptions of COVID-19 threat predict those well-being markers and public health behaviors, which is the question that the authors wanted to answer. And again, we're going to see some simple regression, multiple regression, and path analysis. And last is, are the effects of each type of threat on the outcomes equal? And this is going to lead us to talk about some really cool and unique features of SEM, which is the fact that we can put equality constraints in our models and do model comparisons in order to answer these types of questions. All right, there's one more thing I have to bring up, which is software. There are lots of commercial and non-commercial programs for doing SEM. I've listed here some of the most popular R packages, if that's sort of your preference. In SAS, there's ProcKalis has been around for a long time, so they are packed with good features. And since version 15 of JMP Pro, that's when we introduced a brand new platform, SEM platform, to our software to estimate structural equation models. And the nice thing about JMP Pro is that we're able to estimate our models and specify them directly by using the path diagrams, which I think is very intuitive. Yes, there's definitely literal. Literal is where SEM pretty much started. So that's why I put here, and many more. There's a lot of, there's literal, there's M+ that are very popular, EQS, and so on. So there's a lot of other programs and options out there. The thing is, all of these that we've mentioned, they're all code-based. And so if you're a coder and you want to go that route, that's fine. I think that a really nice feature of JMP is that you can specify the models based on the path diagrams themselves. And so we're going to be able, in this tutorial, to circumvent all of the sort of learning curve of code. And we're just going to go straight into SEM because we can do that. So let's go ahead and start with those examples. And I gotta exit this screen. And so right here, I already have the data open. You can see I also have my little cheat sheet here with the questions that we want to answer. And the first one was about how to measure COVID-19 threat perceptions. And the data table that I have actually have a lot of variables, right? There's 238 columns in this data table. We have 550 rows. And I'm familiar with this data, of course. And so I happen to know that these first 10 variables here are the ones that correspond to this survey that we saw. And so I'm going to use those to use our SEM platform. So I'm analyze multivariate methods, and we're going to look at SEM. And immediately upon launching, we have a default model, right? And the default model is portrayed by the path diagram. So notice every single one of our variables has a double-headed arrow, suggesting that as a default, we acknowledge that they all have a variance. Of course, this model doesn't show any covariance between the variables, which is a very strict assumption, right? We expect these things to covary. So a few things. First, notice on the top here, there's some details, including the degrees of freedom. And we've talked about how that value, where it comes from. This right here tells us the number of freely estimated parameters in the model. And we have 10 manifest variables in this case that are in our model. So we just get some details over here. And you're going to find different ways in which, obviously different software is going to work differently, but we're going to measure these perceptions by leveraging the information on the variables that we do observe and inferring that there are underlying latent variables that cause the common variation, right? So we're going to specify latent variables. Now, the first 5 variables here, again, I'm familiar with the data, so I know that those happen to be the answers to the questions related to realistic threats. So here, in order to add a latent variable, I've selected those variables, and I'm just going to customize the name of the latent variable down here. So I'm going to call that realistic for realistic threats, and I'm going to add the latent variable. And by now, this should be something that you guys all recognize. So the realistic threats or perceptions of realistic threats are now represented explicitly by the circle, right? That latent variable. Notice here that there is a 1 on that first loading. And that number, what it means is that that edge is not freely estimated. In fact, that loading is being fixed to the value of 1. And the reason for that is because we have to set a scale for this latent variable. In other words, we just wouldn't be able to estimate, the model wouldn't be identified if we don't place some constraint, right? And that constraint can be any of the loadings can be fixed to a known value like 1. Another thing that we could do is actually fix the variance of the latent variable to 1. What it is that we choose is completely arbitrary, but as a default, most software programs will actually fix that first loading to 1. That's a very common constraint. So let's go ahead and select the other variables that I happen to know that represent symbolic threats. And so I'm going to add that latent variable. Once again, we see that the first loading was fixed to 1 as a default. And this, we could already run this model. This is a confirmatory factor analysis, but notice that there's no arrows connecting any of these variables on top to the variables on the bottom here. And that is a very strict assumption, right? This is equivalent to saying I have 2 factors and they are orthogonal. There's no covariation between them. And even though that might be what you expect, you always want to test that assumption. I mean, the chances that the correlation between 2 variables is really truly 0 is was a strong assumption, and so likely not going to happen. And so I think the most common way to specify a confirmatory factor analysis is in fact to put a covariance between the latent variables. And of course, in this case, we expect that those who perceive more realistic threats are also more likely to perceive some sort of symbolic threats. So we're going to click this double-headed arrow to just link the 2 variables with a covariance. And this right here is the path diagram that you would encounter no matter, the textbook or the software. This is what a 2-factor confirmatory factor analysis would look like. And what it's doing is it's leveraging the observed variables, the information that we have there, to capture latent variables that are going to account for measurement error, because they're really just capturing common covariation across the observed variables. All right, so we can just call this CFA, and this is a 2-factor or 2 latent variable. And we can run this right away, and we get all our estimates very quickly. But before looking at those estimates, someone was asking about model fit and how we go about, learning about the fit of our models. And so we have a model comparison table here, and the statistics that are in this table, you're going to find them across all. All right, so but notice that there's also something peculiar here. We've only estimated 1 model, right? We said we wanted our confirmatory 2-factor model, but there's 3 models in this list. And so the reason for that is, and again, all SEM programs, we're always going to estimate a couple of models that are going to help us be sort of like our baseline comparison, so that we have something to compare our own specified model against those baseline models. So very briefly, I'll tell you about the unrestricted model. I'm just going to reset the specification up here. And actually, what I'm going to do is I'm going to show you, if I select all the variables and just put covariances across all of them, this right here is what the path diagram of the unrestricted model would look like. That's why it's unrestricted. Basically, it has 0 degrees of freedom, right? Because we're giving it the variance covariance matrix of these data, the sample data. And then we're saying we're going to estimate every single one of those variances and covariances. So there's going to be 0 degrees of freedom. And it also means that we're going to have perfect fit. It's perfect, but it really is kind of like a silly type of perfect fit, right? Because we're not testing any hypothesis. All we're saying is, here are the sample data, go ahead and give me back all the variances and covariances. It's basically not very interesting, but it is very helpful for determining what is the perfect fit, right? What is the likelihood of a model that has perfect fit? And so you can see here, one of the statistics that are very common is the chi-square statistic, which represents the misfit in the model. And so not surprisingly here, it's 0 for the unrestricted model, because again, it's sort of quote unquote perfect fit. The model has 0 degrees of freedom. And we also have another, some other fit indices on the right. This first one is called the Comparative Fit Index. It ranges from 0 to 1, where 1 is the best possible value. So the unrestricted model has a CFI of 1 because it's perfect fit. The RMSEA is the root mean square error of approximation, and that value also is bounded within 0 and 1. And in this case is the opposite of the CFI, because here we want the value to be as small as possible. So we have a 0, which is the smallest amount of the RMSEA. So that's what we would expect from a perfect fitting model. That model is now going to be in contrast to the independence model. And here, what the independence model looked like is exactly what we started with, okay? So this one right here, where everything is supposed to be independent, nothing is linked to anything else. That is the independence model, and we expect that to fit very badly, right? It's going to have poor fit, and in fact, the chi-square, which is a measure of misfit, is almost 2,000 units. So it went from 0 to about 2,000. So yes, this is a very poorly fitting model, because remember those slides I showed you, it suggests that all of the off diagonals are 0. And clearly that is not the case according to the data. And you can see the CFI is actually 0. It's really, really bad. And the RMSEA is 0.27. That's also really bad. A lot of simulation work has shown that the RMSEA should be at the very least 0.1 or lower. Okay, so that's really a poor fitting model. The values to the right, by the way, this is a confidence interval around the RMSEA. Okay, so now we have a really good fitting model, a really bad one, and now we use that information so that we can gauge how good our own model fits, right? First, we can see the chi-square statistic. So we no longer have something close to 2,000. We now have 147. So that's interesting. But remember, we have degrees of freedom associated with that chi-square. And so we can get a statistic that tells us that this chi-square is statistically significant. The thing about chi-squares is that they are going to be influenced by the sample size. And again, a lot of simulation work has shown that once you go above 200 or 300 observations, in our case, we have 550, nearly every model is going to have a significant chi-square. So we no longer can rely on the chi-square. Now, really important to understand that chi-square here is, again, a measure of misfit. So significant chi-square is telling us you have a significant amount of misfit. And so that's bad. This is one place where we do not want to have a significant chi-square. But because we have a very large sample, we're really going to rely on these fit indices that are very common in SEM, and those are the ones that most folks would rely on in this type of situation. The CFI is always recommended to be about 0.9 or higher. In this case, it's 0.93, nearly 0.94. That's really good. And the RMSEA is definitely less than 0.1. So we're pretty happy with that. That suggests our model fits well. Now, I know I'm giving you a lot of information here live. I want you to know that I will, in the slides, I'm going to direct you to some resources where you basically have like cheat sheets on what all these numbers represent, so that you don't have to hold all of this in your memory. There is a place where I can direct you where you can get all of these notes. Okay, so now that I know the model fits well, which is the first thing I need to check, I can go ahead and interpret its results. So I'm going to look at the results of the model. And when it comes to confirmatory factor analysis, we always want to focus on the standardized solution. That's basically The standardized values are those that we would have obtained if every single variable had been standardized, like in a z-score metric, prior to launching the analysis. Okay, so here I'm going to right click and I can show the standardized estimates. And those are going to be much easier to interpret. So the factor loadings are in a correlation metric. And so they represent the correlation of each observed variable with the latent variable. So of course, we want these to be high. And from factor analysis literature, we usually want at least a 0.4 or higher, right? That looks good for these particular items. For the symbolic threat, we also see that we have factor loadings that are substantial. So that looks pretty good. And notice that the two latent variables do correlate at around 0.4. And because it's a standardized solution, the variance of those latent variables is 1. There is a particular option in JMP that kind of puts a lot of statistics together in one place that allow you to assess how good are all of these questions individually and how good are these latent variables as a whole. If you use other software, you're going to have to kind of find those statistics in different separate places. But here, I have an option here. There's assess measurement model. And when I click on it, there's this sort of dashboard output where you can see first, there's something called indicator reliability. And this is basically information that's unique to each of the questions in that survey, right? The indicator reliability is a squared standardized loading. And there's a threshold here that we include, this little line that's just a suggestion, right? We always want to be very careful with cutoff points. It's a suggestion as to what you want the indicator reliability to be. So it seems based on this plot, all of these bars are simply the values over here plotted on the right. And it suggests that we're actually doing a pretty good job, especially with the symbolic threat questions, right? And for the realistic perceptions of threat, they're also good questions. There's a couple that are sort of around the cutoff point, but again, that's still acceptable. And so we would agree that this is an okay survey, or these are good questions for measuring these two types of threat. On the right-hand side, we have something called composite reliability. Folks that are familiar with survey creation oftentimes have heard of coefficient alpha or Cronbach's alpha, and that's another composite of reliability. But the sort of the standard in the literature, the best composite reliability out there, the best estimate is in fact omega, and that's what we provide here. And again, there's a little cutoff point or bar just to show you what is suggested. You want it to be at least around 0.7. And in this case, both the realistic and symbolic threat have that, meet that value, that minimum. So this again is positive news for the survey. And I guess there's, this is to be expected given that that the data were published right in that one article. Just to be also very clear, the composite reliability is basically how reliable would my measurements be if I were to grab, for example, all of those questions that were the realistic threats. If I grabbed all of them and created just an average and then use that average, how reliable would that average be? That's what this is referring to. All right. Okay, so there's other information here. I'm not going to have time to cover that today, but just know that the composite reliability, the indicator reliability, they're very useful just to know if we're doing a good job with our survey. Validity is really important, but again, we don't have time to talk about this, but you can always look into it. It's very, very important for survey creation. All right, so that is basically our first question. How do we measure those perceptions? Is through a confirmatory factor analysis model. And in SEM, so much of SEM is based on model comparisons. And so it
Laura,
might be.
Can I cut in?
Oh, yes, please.
You've got a couple of questions piling up in the chat if you want to take a look.
Let's see. I kind of lost the chat. I guess it's, oh, I see it now. Thank you. So the -2 log likelihood is asymptotically chi-square with degrees of freedom. Yes, so there is a direct connection between the log likelihood and the chi-square. That is correct. And in fact, we're going to rely on that in order to compare models, because we can do likelihood ratio tests, also known as chi-square difference tests. So yes. And then they say, how do you observe for deviations from multivariate normal? You definitely, that's probably something you'd want to do before, in more like a pre-processing type of step, where you would take a look at your multivariate normality. It could be done with Mahalanobis distance or some other multivariate techniques that allow you to look at multivariate normality. And another question is, are the RMSEA confidence intervals found using Wold approximation? Confidence intervals on the individual coefficient parameter estimates. Let's see. I implemented that a long time ago. I know that they're not, it's most likely yes. They're not bootstrapped or anything like that. So I believe the answer is yes, but I'd have to double check. Are there corrections for deviation from multivariate normal? Yes. So in some, again, this kind of depends on the software. If you have ordinal data or categorical data, there is software that allows you to explicitly say, you know, the distribution of this variable is it's count data, or it's you know, whatever the circumstance might be. In this case, we're sort of just sticking with the most common and simple approach, but yes, there are corrections, and in fact, there's also a correction. It's called the Satora-Bentler correction, which allows you to still stick to the maximum likelihood multivariate normal assumptions, to still do estimation that way, but there's a correction that can be done in the case, and people rely on this a lot when they have data that are not looking so normal. Again, it's a Satora-Bentler correction, and using that sort of alleviates the problems from the deviations from normality. Thank you for pointing that out, Tom. I do have the chat on a different window now, and so it's hard to see the questions. But I know we don't have a ton of time left, right? We have 12 minutes. And so what I'm going to do is just show you that, again, model comparisons are at the heart of SEM. You don't just come into SEM with one theory and only test that theory and say, oh, it fits good, it fits well, I'm good, I did a good job. The whole process in SEM would be, okay, let me now test that theory against an alternative, and might I find more support for the alternative? I don't know. In this example, it would be fairly intuitive to think, do we really need two dimensions to measure these perceptions of threat? It might be that I can just have one latent variable, right? And I'm going to call this threat, perceptions of threat. And I can have this type of model where it's just the one threat latent variable. And so I just call that here CFA. I'm going to call this one factor. And I can, oops, factor. And oh my gosh, there we are. And I'm going to run this model. And the models was fit. I see the model down here. But notice in the model comparison table, I'm able to, well, first I can look at the fit indices, and you can see that they dropped by a lot here. The CFI is no longer acceptable, neither the RMSEA. But as you know, there was a question in the chat asking about the log likelihood. And so these two models are nested models. Again, we're going to have the notes that I'm going to share with you have details on nested models. But when your models are nested, you can compare them with, thanks to the likelihood. And so here I'm just going to click compare selected models, and I'm able to see the change in chi-square with the change on degrees of freedom, and I get that chi-square test. Again, we do have a large sample size, so we definitely want to rely on the change in these fit indices as well. And we definitely don't want to see change that is larger than 0.01 in either of these. And so this is a very large change, and we would say, nope, the one factor model is no good. We really need those two dimensions in order to capture these constructs. All right, so model comparison is very important. Okay, so that's for for the CFA. The next question was, do those perceptions predict some other outcomes, right? And a lot of times, if we have a good survey, for a number of reasons, it might be easier to say, okay, those were my questions. I know that they're good questions. I'm just going to create an average of them. And I'm going to use that average for secondary analysis. And, you know, depending on the circumstance, that might be okay. So to show you an example, I actually have that. I have that example here where I have already created averages between the, the first 5 indicators of the realistic threats and also for symbolic threats. And so let's see. I have here, I already have a saved script where I actually have those averages. Notice they're right here. Okay, there's the realistic. I put realistic 5 because there were 5 items that were averaged, and the symbolic threats. And now these are rectangles because I kind of made them observed variables, right? Because I just averaged all of the columns in the data. And so just as a demonstration, I wanted to show you how would we use those threats as predictors of a number of outcomes, right? We have anxiety, negative affect, life satisfaction, and also whether or not people are adhering to public health behaviors that were recommended by the CDC. So by linking those with that one-headed arrow, that's my regression. And I'm going to covary these variables here because I'm not going to assume that they are orthogonal. I think they covary. I have a little shortcut here to covary the endogenous variables. You now know what that term means. It's all of these variables over here are endogenous. And I'm going to go ahead and run this model. And so this is an example of a multivariate or a multivariate multiple regression, right? And I'm going to move around the diagram a bit so that I can focus on a very specific part of this model. So I'm going to move this around and I'm going to hide the covariance. Okay, so notice, for example, that both realistic and symbolic threats are predictors of anxiety, and they have a positive coefficient. This over here on the left, we see that this are statistically significant. And the point here is that those who are more likely to experience both realistic and symbolic threats are also more likely to report higher levels of anxiety. So that's intuitive, right? And what I want to show you is contrast these results with an actual regression that I fit on just an ordinary least squares. And I have the results right here. And I'm going to put them right next to the diagram so you can see. The coefficients here is 2.84, or, they're the same coefficients as in the SEM model, all right, 1.05, they're the same ones. And the intercept is also the same. I can look over here for the means of anxiety. Notice this is the same coefficient as well. So what have we gained so far? If you really wanted, you could run an ordinary least squares regression, right? Multiple regression, and you can run it, 5 times in order to obtain all of these estimates. So if you don't have missing data, you're going to have the exact same results. The thing is that in SEM, we are also able to do more than that. Okay, we can test very interesting questions, such as, are the effects that these 2 types of threat pose on anxiety, are those 2 effects equal? Are they equivalent in magnitude? Now, we can just eyeball it and it looks like this one's bigger, right? The 2.8, but we don't know that. So we want a statistical test for it. So I can use these button here to set those to be equal. We use a little label to imply that they're equal. And I'm just going to run that model. And I have that model here. Notice now the estimate is 1.7, but what is really useful is I'm able to grab both of those models, the first model, and compare it against the one that has those equality constraints. And by getting, oh, sorry, I must have done something wrong here. Okay, so the thing is that by looking at a comparison of these, and what did I do? Okay, by comparing those 2 models, again, the way in which we did it before with the chi-square And in this case, it's very simple. We know that the chi-square is increased by 8.6. And with 1 degree of freedom, that is significant. So what this implies is that the model where the constraints of equality were placed, those constraints are basically increasing the misfit of our model in a statistically significant way. And therefore, we're able to say, no, this model does not fit as well as the other one. And so I'm going to trust this model best. And I'm going to be able to say now that the effect that realistic threat has on anxiety is significantly larger than the effect that symbolic threat has on anxiety. All right, so those types of questions where we have, we can test whether effects are equal to each other, and we could do that for, for each of the effects that we have in this model. And I know we have 3 minutes. Is that what you were going to say, Tom?
Yes.
All right,
And
I'm going to wrap it up.
And there's
Yes.
one more question still in the chat.
Okay, so bad we're running out of time. We have been answering these questions, and we actually even answer question 3, right? Are those effects on each time of threat equal? And we saw that for anxiety, the effects are not equal. Question, model 2 has a smaller AIC, indicating that model 2 is better. That's, oh, and I closed the window. So in the interest of time, the answer is, if that is the case, then the AIC would suggest that the second model is better. I might have made an error in the specification of the model because I also got that warning. So I'm not sure, but yes. So if the models are nested, the standard is to use the likelihood ratio test, and that's what we're going to use to gauge which model is better. When models are not nested, then we rely on things like the AIC and the BIC. I'm sorry that, yeah, I have 2 minutes, so I can't really get to the bottom of that, but it might have been that I made an error in what I was doing. Another thing I want to say, I want to make sure that I say this though, is if we went through the trouble of getting that survey and all that good stuff, the last thing we want to do, I think, is to actually create averages. What we really want is to use the latent variables in our analyses to explore their associations with other variables. So here's an example where we can actually use the latent variables to predict anxiety, not their composites. And what that allows us to do is get estimates of these regression coefficients that are unbiased or unattenuated by measurement error. And so fitting this type of model is going to get us estimates that, depending on how much error is in our observed variables, if there's a lot of measurement error, then these estimates are likely to vary from what we would have obtained with the averages. So not only can we capture the latent variables, but we can also measure, model them, right, directly in SEM. Okay, so that's the end of that. And I did want to show you some examples in the literature. This is in the slides in the materials that are online. And it's just examples from HSI research, right? Here's SEM to predict cabin safety outcomes. And hopefully now these path diagrams make more sense to you. This is one where they were just looking at associations between all of these latent variables, looking at their correlations. This is with artificial intelligence-based self-service technology. If they were testing, user experience, what are the things that influence user experience? And you can look at these with a little more time on the notes that are available online. But again, we're just looking at things like trust, right? How do they influence intention to use the system? And so there's a number of examples. I'm just gonna go through all of these and just skip through to the thank you part. I know that I've completely exhausted the time. I'm sorry. I hope I've answered questions along the way to where you don't feel like you have many left. if there was more time, I'd be happy to stick around and continue to answer those. But these links have all the resources we talked about too, so that you can consult those.